Hi, everybody. So in today's lecture, I'm going to talk to you about electric charges and electric fields. So first of all, a little bit of history. There's a lot of applications to electricity and magnetism, both macroscopic and microscopic, but it all got started probably with the Chinese as early as 2000 BC. So those documents suggest that they observed magnetism probably from natural rocks like lodestone as early as 2000 BC. And then there's recorded work done by the Greeks of electrical and magnetic phenomena as early as 700 BC. Now, with the Greeks, they did some experiments with natural rocks and ores known as amber and magnetite. And after amber is rubbed, it attracts small objects like feathers, and we're going to talk more about that later. So the word electric that we use now, and of course the word electron, comes from the Greek word for amber, which is electron. So that, of course, reminded me of my big fat Greek wedding. Now, there's two kinds of electric charges, and there are positive and negative charges. Negative charges are the types possessed by the electrons in the atom, and positive charges are the types possessed by protons in the atom. And just as a quick reminder, of course, in the atom, the nucleus of the atom, or the core of the atom, is made of protons and neutrons, the protons positively charged and the neutrons neutrally charged. And then the nucleus is orbited by the electrons, which have that negative charge. Now, charges of the same sign repel one another, and charges with opposite signs attract one another. And objects are electrically neutral if they have equal amounts of positive and negative charges. So a neutral atom has the same number of protons as it does electrons. Electric charge is always conserved in an isolated system. And what that means is that if you have a positively charged object, it's not because the negative charges in the object were destroyed or anything. It just means that those negative charges were transferred somewhere else. And you can create that transfer of charge via electrical conduction, or you can do something as simple as rubbing two objects together, which is called triboelectricity. And that can also transfer charge from one object to another. And then, of course, once you've transferred that charge, then you can have a total charge on the object. And then those charged objects can cause repulsion and attraction to other charged objects. In the triboelectric scale shown here, it shows you which way an object will be charged. Now, if rubbing it causes a positive net charge to the object, then that means that that object has given some of its electrons to the other object. And if an object has a negative net charge, then that means that that object took electrons when it rubbed the other object. So in terms of positively charged things, hair, human skin, rabbit fur, glass, human hair, those have a tendency to end up positively charged. And things like plastics, such as Teflon or PVC or polyethylene, polyester, those kinds of things have a tendency to gain negative charge and become negatively charged upon rubbing. Now, we have a whole bunch of demos that we do in class. I'm sorry I can't show them to you since we're not in person, but we have glass rods and plastic rods that we rub with things like fur and silk and show that those things then become net charged, mostly by placing them on pivots and holding opposite and like charged objects up to one another to show that it turns on the pivot. But for example, if you have a glass rod rubbed with silk, let's go back to our little chart here. You can see that glass has a tendency to become positively charged, and silk is further down on that triboelectric scale. So it's going to become negatively charged if it rubs glass. And so that means that you're going to have electrons transferred from the glass to the silk, and then the silk becomes negatively charged, and an equal positive charge is left on the rod. Now, you've probably all played with this and experienced this in your own lives. I'm sure all of you have played with rubbing balloons on your hair and then showing that your hair sticks to the balloon. So if you've ever wondered why that happens, it's because electrons are transferred during the rubbing of the balloon on your hair, and the balloon picks up more electrons, and so it becomes negatively charged. And then your hair has the net positive charge because the negative charges were transferred from your hair to the balloon. Okay, so then they're equally and oppositely charged. And then what happens is you can hold the balloon away from your head and it will attract the hair. So that's a really common demo that you can do yourself. And then in class, we take rubber rods, for example, and rub them with fur, and then they become, the rods become equally negatively charged, and then we can show that they repel one another by placing them on a pivot. Now, charge is said to be quantized, and what that means is that the smallest unit of charge that something can hold is the amount of charge held by an electron or a proton. This is under natural circumstances. So we're going to use the letter Q, or big Q or little q, depending on whether I'm talking about a big charge or a little charge, right? To stand for charge. And whatever amount of charge is transferred, say from the balloon to your hair, that's because a certain number of electrons were charged. And so we can write the amount of charge that something has as an integer big N times the charge on a single electron. So that we can say that the amount of charge something holds is equal to plus or minus N times E. And the plus or minus will depend upon whether or not it picked up electrons or it lost electrons in the rubbing, for example. Now, lots of times the amount of charge that's transferred when you rub something, or when you transfer charge via conduction or any other method of charge transfer, it's actually a lot of electrons. And so that means that N is an integer, but it's a really big integer that we would express in scientific notation, like, I don't know, 1 times 10 to the 9th, right? Charge is transferred. So from our macro scale point of view, even though charge is quantized, which means it comes in little tiny packets, right? And the little tiny packet sizes that it comes from is the charge on an electron. Even though it is quantized, it looks continuous because the value of the charge in an electron is so small. We're going to call E, lowercase e, the amount of charge held by an electron or a proton. And that amount of charge is 1.6 times 10 to the minus 19 coulombs. Now, we're going to talk more about this later, but the coulomb is the standard unit of charge in SI units. So this is a very small number. And so we only saw the discrete effects of charge relatively recently, starting in like the late 1800s, early 1900s is when we started learning about the quantization of charge and really quantifying it. Now, an electron has charge minus 1.6 times 10 to the minus 19 coulombs, and the proton has charge plus 1.6 times 10 to the minus 19 coulombs. And let's think about that for just a second. 10 to the minus 19 means the decimal point, and then 18 zeros, and then a 1 after it. Okay, so this is a tiny, tiny little number. So here it breaks down in an atom. You have electrons, protons, and neutrons. And of course, the neutrons are neutrally charged, and then the electrons are negatively charged. If you break it out in terms of lots of significant figures, the electron has minus 1.6021765 times 10 to the minus 19 coulombs of charge, and the proton has plus 1.6021765 times 10 to the minus 19 coulombs of charge. Now, the masses of the protons and the neutrons are very different. I'm sorry, the protons and the electrons are really different. The mass of an electron is about 1,000 times less than the mass of a proton. The mass of an electron is 9.11 times 10 to the minus 31 kilograms, and the mass of a proton is 1.67 times 10 to the minus 27 kilograms. And you can see that the mass of the proton and neutron are about the same, okay? Let's talk about the different kinds of materials that they are. Some materials transfer charge easily and move charge around easily, and some materials don't. The ones that move charge around easily are called conductors. So in an electrical conductor, the materials, these are materials where some of the electrons are actually what we call free electrons. And that just means that the electrons can move pretty much wherever they want within the material with freedom, right? So they can hop from atom to atom, neighboring atoms. They move around very easily throughout the whole lattice of the material. And this is why we use them in electrical wiring in houses, for example. So in a metal, the metal ions are in the lattice, right? They form a grid, sort of. And the electrons then move around the lattice. These free electrons move around the lattice. Now, it's important to understand not all electrons are free to move. Only the ones that are in the outermost energy levels that are the weakest bound to the atom are free to move around. And this is usually between 1 and 3 electrons per atom. And of course, metal atoms have, for the most part, a lot more electrons than that, okay? So only 1 to 3 electrons are free to move around the lattice in these things. Examples of good conductors include copper, aluminum, silver, things like that, gold. These are all good electrical conductors. Now, when a good conductor is charged in a small region, like let's say that you charge something by conduction so that you add a net charge to, say, the left-hand side of a conductor, then what happens is the charge wants to be the same. It wants to be uniform across the whole object. And so the charge will quickly move around and redistribute so that that happens, okay? And that's just because, you know, likes repel and opposites attract. And so if an electron sees, for example, a positive charge on this, a net positive charge on one end, it will move over attracted to that. And if it sees a net negative charge on one end, then it'll be repelled away. And so that charging causes the electrons to move. Now, electrical insulators are the opposite of electrical conductors. Electrical insulators are materials where the electrons do not move freely at all. They're pretty much bound to the atom or molecule that they're sitting with, right? So these electrons don't move freely through the material. So examples of good insulators are things like glass, rubber, wood, amongst a lot of others. Now, when you charge an insulator in a small region, that charge is unable to move to other regions of the material, right? So, for example, in the example that I gave of rubbing the balloon on your head, if you rub the balloon on this side of your head, the hair on this side of your head wouldn't really be affected by that. It wouldn't necessarily feel that charge, right? Have charge transferred. It's only the hair on this side that's going to be all charged up. And that's because your hair is an insulator. And so if it gets charged in one area, that charge doesn't move around easily. Now, there are materials called semiconductors, and we have a lot of these in our computers and cell phones and other electronic devices. And they have electrical properties that are somewhere between those of insulators and conductors. So what that means is, in order to get an electron free in an insulator, you have to give it a lot of energy, okay? You have to really rub it hard, or you have to apply a large electric field to yank things off. In other words, a big voltage. Or, you know, you have to give it a lot of energy in some way. Now, a semiconductor, it takes energy to get that electron free and to move it around, but it doesn't take as much energy. We'll say it takes maybe 1/10 to 1/100th the amount of energy that it takes for an insulator, okay? So semiconductors can be conducting if you apply enough energy to the system by maybe heat or maybe electrical energy of some kind. Okay, if you do that, then those electrons can freely move and they'll behave more like a metal. But there's a threshold, right? There's a threshold amount of energy that you have to overcome. Now, there are some natural semiconductors out there, materials like silicon and germanium, but you can also take materials that would otherwise be either metals or insulators and then do what we call dope them with extra charge of one type or another, and then they can behave like semiconductors when you do that. Now, there's a really nice graphic, kind of a way to wrap your head around this concept of the difference between conductors, insulators, and semiconductors, and that's called the band gap model of materials. So taking one extreme, if you look on the far left at the insulators, those things take a lot of energy to free the electrons, okay? And it can be conducting. It just takes a lot of energy. Think of things like a bolt of lightning. Air is not normally conductive, but if you have a large enough field, a large enough voltage between the clouds and the ground, yeah, you can get it to conduct. And then you see the electrical strike of the lightning bolt. Now, on the far other side, metals don't really need any help at all, okay? You don't really have to give a metal electron any energy if it's already a free electron in order for it to move around, okay? So this is kind of visualized by thinking about a conduction band, which is where the electrons have to be in energy in order to move freely, versus a valence band, which is where they are when they're bound tight to their host atoms. So if you see there's an energy gap in between the insulator's valence band and the conduction band, okay, it's normally empty, but if you give it enough energy, it'll jump up there and then it'll become a conductor. In the metal, we don't think of there being any gap in between the valence band where it's bound tight to the atom and the conduction band. In other words, the electrons that are on the outermost energy levels of a metal atom, the ones that are the weakest bound, those are free to move around anyway. And so we say that there is no band gap for the highest energy electrons in a metal. But in a semiconductor, there is a gap, right, between the valence band and the conduction band, but it's not a lot of energy. Like I said, it's maybe a tenth to a hundredth of that what you would find in an insulator. And so if you just give it a little bit of energy, it'll hop on up there and be a good conductor. So that's kind of one way to wrap your head around all that. Okay, moving on to a slightly different topic. We've talked about how you can charge objects by rubbing, and that's triboelectricity. Tribo is from the Greek word tribos, which means to rub, okay? But you can also do what's called charging by induction. When you charge by induction, you don't have to have physical contact between the two objects that you are using to do the charge transfer. So let's imagine for a second that you have a metal object, okay? And just for, ease of drawing, we'll call it a neutral metal sphere, okay? So this one has the positive ions in the cores, and then an equal number of electrons kind of roaming around, okay? Same number of positive and negative charges. Now, what we can do is we can bring something that has a net charge, say it has a net negative charge, right, near that neutrally charged metal sphere. Okay, what happens in that case is that like charges repel one another, and the electrons like to move around, right? And so if you bring a charged object near a metal object, then what'll happen is the electrons in the metal object will be repelled from that net negative charge that it sees, and they'll scoot on over to the other side of the metal object, as is shown in this little sketch. So it kind of redistributes where the charges are. Now, if you were to ground those electrons, that metal sphere, which means that you're going to hook up a conducting wire in between your metal sphere and then some source of big source or sink of charge. Lots of times when we think of grounding, we think of the extreme thing where they hook up lightning rods, where you drive a big metal stake into the ground outside. And then the ground and the groundwater and all that kind of stuff acts as a net sink of charge, source or sink of charge. So you can think of the electrons as kind of disappearing into infinity when we say hooking it up to ground. So these electrons are repelled, and then they move out of the conducting wire into the ground to get away from the negative charge that's over here, okay? Now, if after you do that, you then disconnect that wire while still holding the negative rod near, then what'll happen is you'll leave that metal sphere with a net positive charge, because the electrons ran away from the electric charge here, went into the ground and disappeared, right? And then you have this net positive charge left in your metal sphere. So what that means is that you have induced a positive charge in the sphere, okay? That's charging by induction. You can then take the rod away, right? The negatively charged rod away, and you'll still only have, a net positive charge in that sphere because you've driven the other electrons into the ground. Now, if you're going to do this, it's important to remember the step that you've got to disconnect the grounding wire, okay, while the rod is still near it. Otherwise, what'll happen is the positive charges will pull negative charges back from the ground if you don't disconnect that wire before you move the rod away. So it's very important that you have the negative rod here while you're grounded, and then leave the negative rod there as you disconnect your grounding wire in order to achieve a net positive charge on your metal sphere. And you can do the exact same process if you have a positive charge. What'll happen is you have the positive charge, positively charged rod, right? You have it grounded, okay? The positive charge will pull negative charges in from the ground, and then you'll have a net negative charge once you disconnect the grounding wire. So you can do either way with that process. Now, you can also get charges to rearrange even if you have a material that's, say, normally an insulator, okay? You can do that. And also, you don't have to have the grounding wire there in order to experience this. So you might have played around with this a little bit at home too. Have you ever rubbed a balloon on your head, transferring charge from, the balloon to your hair? You see your hair stick up. And then have you ever taken that same balloon and stuck it on the wall and it'll stick to the wall? Okay, that's exactly because the charges in the wall are rearranging in response to the net charge of the balloon. So let's say what happens here is that you have a positively charged object, right? Like a balloon or something that you bring near to the wall. And then in the wall, what'll happen is that the negative charge will want to be near the positive charge of the objects that's right next to it. So the charge will rearrange, okay? And then the positive charge will be repelled in the wall, okay? So you're going to have a surface charge, a net surface charge that's negative, and the positive charge will move into the wall and try to get away from the surface where this positive charge is here, okay? Now that doesn't mean that your wall has a net charge. You can see here that in these little pairs, you have negative positive pairs, okay? You have negative positive pairs within the wall. So the wall doesn't have a net charge, but you can still see that attraction because of the rearrangement of the charges in the wall, okay? So that's what's happening there. And if you've never done the balloon on your hair thing, or rubbing the balloon on your hair and then sticking the balloon to the wall, you should immediately try this. It's a cheap physics demo that illustrates a lot of great concepts for you. Okay, thanks. I hope you enjoyed that, and I'll see you next time.